Sandra, I think you'll be on YouTube with your head down. They might not recognize you then. I know. Oops. I had ugly old green things and. Ooh, 10:07. All right. Today we'll finish up on these, looking at these differential equations that we can separate with the y variable on one side, the x variable on the other. This is section 9.3. And then we'll be going on then to start the last chapter, section of chapter 10. Okay. All right. So 9.3, separable, differential equation. Okay. All right. So I'm just going to continue to do a couple more examples of this so you can get a feel for how this works. So let's just look at this one. Y prime equals x squared times y. Now remember, what we are solving for is we are solving for y. With these, we don't solve for a number, we solve for a function. Okay, now, if the equation is presented in this form, where we have y prime, you want to immediately, as your first step, rewrite it using that, what's called Leibniz notation. So you want to rewrite it as dy dx equals x squared y. That's your first step. Okay. And then you do a combination of multiplying and dividing so that all the things involving y are on one side and all the things involving x are on the other side. So in this case, I'll divide both sides by y and multiply both sides by dx, and I'll get this. 1 over y dy equals x squared dx. Okay. So now this is called, they're both separated. And so what we do next is just take the antiderivative of both sides. So we put the integral sign in front of each side. Okay. The left side is going to give us the ln of the absolute value of y. and the right side is going to give us x to the third divided by 3, and we do have to have 1 plus c, so we just usually put it over there on the right-hand side. Okay. All right. Now, in this case, and in problems, I will let you know if I'm looking for what's called an explicit solution. In this case, I would want to look for an explicit solution. Now, so this is hearkening back to when we looked at logarithms here. That we know that the natural log has the base e, the number e, even though it's not written. And basically, I believe I mentioned this in class, a way to approach this problem is to do that thing that I call the spiral, to rewrite it. So basically, we start with our base e, even though it's not written, it's assumed to be that. Then we take this entire expression on the right-hand side, and we put it as an exponent. The x to the third over 3 plus the c. We write our equal sign, and then we continue on the spiral, and we end up with the absolute value of y. All right. Now, why don't I just switch the sides of this so it looks a little bit more natural? Okay. All right, so we're almost there. What I'd like to see you do next, then, is do a little bit with the rules of exponents to rewrite this right-hand side a little bit. We know that when we have two exponents that are adding together, like these two exponents are here, x to the 3 over 3 and the c, they're being added together, we know that we can rewrite it with that same base, except they'll be multiplied. The two terms will be multiplied. So we can rewrite this as e to the x to the third over 3 times e to that other part of the exponent, e to the c. Okay. All right, so that's just from rules of exponents. Okay. Now, I talked a little bit last time about this kind of this funny business where remember this C here, it stands for any real number, okay? It can be any real number. So look at this expression down there, the base E taken to any real number, all right? What we basically get is, we basically get any positive real number when we do that, okay? Because C can be any real number, both positive and negative. So when I raise the base E to that, I'm going to get any number that's positive, all right? So therefore, I'm going to rewrite this E to the C power as another general constant, but so I have to give it a little bit different name. I'll call it C sub 1. You could call it A or B, whatever it is you wanted to call it. So I'm going to rewrite this as C sub 1 times that other expression, e to the x to the 3 over 3. And it's always helpful then to put off here at the side of your paper then where C sub 1, that new general constant, that equals what we had before, e to the c power. Okay, so we're just kind of cleaning up the notation, really, when we do something like that. So before I go any further, does anybody have any question about that little bit of notation change that you can make when you're just going from one general constant expression to another? Okay. So this is what we have then. We have the absolute value of y is equal to the expression on the right. Now, if we're wanting to solve for y, I need to get rid of the absolute value signs, right? So if I get rid of the absolute value sign on the left, what should I put on the right-hand side? Plus or minus, exactly. I want to put plus or minus here because that absolute value causes it only to have positive values. But when I take away the absolute value, it can have either positive or negative values. So we'll put a plus or minus there. Plus or minus C sub 1, e to the x to the 3 over 3. And now I can also do another cleanup, so to speak, of the notation. Again, this C1, this is actually any positive real number. Now I'm having plus or minus that. So why don't I just put a new notation here, have y equals c, maybe sub 2, e to the x to the 3 over 3 power. All right, where that new notation for a general constant is equal to plus or minus C1. Okay. And then this would be our explicit solution, because we have strictly y on the one side. And it's also called the general solution. Okay, because we still have the general constant. We still have the general constant. That's why it's called a general solution. All right. Now, say we're given what's called an initial condition. So either we're told or we observe experimentally that, say we're told that y sub 0 is equal to 10. Now, what that notation means is this. That means when x is 0, then y is equal to 10. So it's a little bit of a shorthand for doing that. So with that piece of information, we can now solve for a particular value of C2. So we can now solve for a particular value of C sub 2. Okay. So let's plug in these numbers here. We have 10 for the y. We have C2, e, and then x is 0, so that's e to the third over 3 power. So, of course, that's C2 times e to the 0 power, and e to the 0 power is 1. So basically, we found by plugging in that C2 in this case is equal to the number 10. So we can now get a particular solution. We can now get a particular solution. Y is equal to 10 e to the x to the third over 3. All right. Okay. Okay with that problem. A little bit of manipulation there because you're going from the natural log of y to just y. So I recommend using the spiral technique to be able to do that. Okay? All right. Let's look at another example here. With this next example, we have to do a little bit more work in order to get our antiderivative. So here we have dy dt equaling t over y e to the y plus t squared. So that exponent down below is y plus t squared. Okay. All right, now remember, we're wanting to separate the t stuff from the y stuff. So really the first thing I need to do is rewrite that exponent expression with separating the y's and the t's right there. So this bottom part, how will I rewrite that e to the y plus t squared so I can separate them initially somewhat? Yeah, e to the y times e to the t squared. Again, using that rule of exponents that we did just a couple minutes ago. All right. So now I can do a combination of multiplying and dividing. Let's see, if I multiply this part on both sides, and then multiply both sides by dt, I think I'll get everything separated. So if I do that, I get y e to the y dy on the left side, and on the right side, I get t over e to the t squared dt. All right, so they're all separated out. Okay, so now we have to do the antiderivative then of both sides. Now that one on the left, you can see that we're going to have to use integration by parts in order to get that antiderivative, right? So what do we want to have as our u for the integration by parts? Thank you, Keisha. Y. All right, so therefore du is equal to dy. Now our dv then, remember, is the rest of the integral, so it's e to the y dy. And when we do that antiderivative, we just get e to the y. All right. So our left side with integration by parts is going to be u times v, so that's y e to the y, minus the integral of v du. V du. So that's e to the y dy right there. Okay. So let's finish off that left-hand side before we go to the right-hand side. So this is going to be y e to the y minus, and then that antiderivative of e to the y is just going to be e to the y. Okay. So with parts, we got the antiderivative of the left side. Now on the right side, it might be, let me go back up here for the right side. It might be helpful to just, now you don't have to, but it might be helpful to just initially write it as t times e to the minus t squared, where I'm taking the expression out of the denominator, and when I do that, I have to change the sign of the exponent, all right? Now, with that done, what kind of procedure do I need to do to get that antiderivative? Yeah, u substitution, I'm going to let u equal minus t squared. And that's going to work out just fine, because du then is going to be minus 2t dt. And, well, we've got a t dt in our integral, so why don't I divide both sides by negative 2, and I'm going to find that negative 1/2 du can replace the t dt that's in my integral. So we're going to get minus 1/2 du, and then the e to the minus t squared is going to be replaced by e to the u power. And so that's an easy antiderivative. We're going to get minus 1/2 e to the u plus c. And then let's finally replace our u with the minus t squared. And let me write it over here then. So we're going to have minus 1/2 e to the minus t squared plus c on the right-hand side. Okay, and let's see here. So this, let me put a box around this. Now, with this, I don't think we can do any algebra manipulation to just end up with plain y on the left-hand side. So if you can prove me wrong, that's fine. But anyway, this would be fine. This is now an implicit solution because I don't just have y by itself on one side. So it's called an implicit solution. And of course, since I still have the plus c, it's also a general solution. Okay? And that's going to be the end of that problem. All right. Okay, we'll look at a couple more here. This one is actually pretty straightforward, but let me do this one here. I think this one will be more instructive. So here we have y prime equals 3x squared over y. All right, and we're also given an initial condition. I'll give it right up front here. We're told also that y naught is equal to negative 4. So this is our initial condition. All right. So the first thing, what's the first thing I have to do with this before I start doing more separating? Well, even before I do that, yeah, put it in the dy over dx format on the left. And then I'm going to cross multiply to separate the x's and the y's. So what I'm going to have then is y dy on the left and 3x squared dx on the right. It's all separated, so now I'm going to do the antiderivative. And on the left, then, I'm going to give y to the second over 2. And then on the left-hand side, it's going to be 3x to the third over 3. So it's just going to be x to the third. And then I have my plus c. All right. Okay. Okay. Now, we're also told in the problem to find an explicit solution. And remember, I indicated that on the homework, I'll let you know whether I'm looking for, in fact, you've got your hard copies of this homework right now. I will indicate whether I want an explicit or an implicit solution. Okay, so we want to have just y on one side. So what might be the next thing that I might want to do to both sides? Yeah, just multiply by 2. Let's get rid of that denominator. So we have y squared equals 2x to the third plus 2c. All right. Now here then with the 2c, c is any constant. So 2 times c is also going to be any constant. So I can rewrite this as y squared equals 2x to the third plus, say, let's call it c1, where c1 is equal to 2 times that c. All right. So I can do something like that. Now, I certainly could not just decide to get rid of the 2 that's in front of the x to the third, because x to the third is not a general constant. Okay, so I can't do that, but I can do it for this second part. All right. So what would I want to do next then to both sides to isolate the y? Yep, square root of both sides. So on the left side, I just get the plain y that I want. And then the entire other side has to go under the radical, the whole enchilada, so to speak. All right. So radical, 2x to the third plus c1. Now, what we normally do then, remember when we do the square root of both sides with an equation, we do put the plus or minus in front of the radical. Okay? All right, and this, of course, if we were not given the initial condition, this would be our general solution. All right. However, we are given an initial condition. We're told that y naught, when x is 0, y is equal to negative 4. Okay. So let's plug in some numbers here and see what we end up with. So for that y on the left side, I'm going to put the negative 4. Okay, for the moment here, I'm going to keep this plus or minus just for the moment, all right? And then under the radical, I'm going to put in 0 for x, so that's going to be 2 times 0 cubed plus c1. All right. Okay, so therefore that's really plus or minus the square root of c1. So what number would satisfy this? What number for c1 would satisfy that equation? 16. The square root of 16 is equal to 4, so therefore c1 is equal to 16. However, would I still be keeping both the plus and minus here? Which one would I keep? Okay, the minus. The minus. Why? Because look what I have here. I have a negative 4. So I've got to match it with a minus over on the other side. All right? So I'm only going to keep the minus. Only keep the minus for my particular solution. because now we're going for the particular. So be careful about this. So therefore, my answer here is going to be, y equals minus the square root of 2x to the third plus the 16, because we figured out C1 is equal to 16, all right? Now, if my initial condition were y naught equals positive 4, then down here I would have ended up I would not be putting the minus sign down below here, okay, if it had been positive 4. So that's a little tricky. I want to make sure that everybody is clear on that little subtlety that you might have when you do that square root of both sides. They're both explicit solutions, because this has y on just one side and this just has y on one side. So they're both explicit. The top one is the general, the bottom one is the particular. Okay. All right.
I know we can't solve for y, that's
implicit. When we're able to solve for just plain y on one side, then it's explicit, right? And I'll let you know when you can do that, because there are times you just cannot do that, okay? And you just have to settle for an implicit solution, right?
Would you expect to see the model turn over?
Would I expect to use?
To go all the way. They're both.
Oh, I see. If on homework, if you are given an initial condition as part of your problem, then your final answer, Ty, is going to be this bottom one right here. Okay. What's that? Yeah, absolutely. But if you were not given an initial condition, then you would just be stopping here at the general solution. Okay. All right. Let's just look at a population problem here. That population growth model that we had looked at before. All right. So just to what we basically had was this, if we recall, from our assumption. We have this, that the change in population over the change in time is proportional to the size of the population. So that was our scientific or whatever assumption. And this K is a constant that's bigger than 0. All right. All right, so basically now we want to solve this differential equation, okay? So we're basically going to solve for capital P, and it's a function of time, P of T. All right. So we can separate the P's and the T's, again, by multiplying or dividing, so that one is on one side, the other is on the other. If I divide by capital P and multiply by dt, I'll have my variables separated. So let's do that. We have 1 over P then on this side, dP equals K times dt on the other side. So everything's separated out. And then we take the antiderivative of both sides. Okay. Now the left side, of course, is going to be the natural log of P. Now here we have to understand the situation we're in. Normally we put absolute values after the ln, but here we're talking about population, so we're not going to have a negative population. So I'm just going to skip the absolute value, all right? Okay. And then on the right side, okay, I have antiderivative of K, so that's going to be K times my variable T, all right? So be careful. On one side, we're using one variable. On the other side, we're using another variable. And then I have my plus C, my general constant. Okay. So again, we're going to use that spiral technique. We really have a base E down there. So I'm going to rewrite this as e to this power, e to the kt plus c, the entire thing on the right, and then finish the spiral here equals the capital P. Okay. Let me switch it around. So capital P is equal to e to the kt plus that general constant. And we'll do that little trick that we did before where we're going to separate out those exponents there above the e as e to the kt times e to the c power, just with our rules of exponents. And so we have P is equal to e to the kt times e to the c, and then let's just change that e to the c. E is our number or base 2.71. C is any number, positive or negative. So let me just rewrite this as c sub 1. I'm going to put it on the front also, times e to the kt, where that new designation for the general constant, C1, that's equal to that e to the c that we had previously. Okay. All right. Now, okay, so this certainly right here is our explicit solution, and it's also a general solution because we still have the c in it. So why don't I just call it an explicit general solution. All right. Okay. Now, suppose that we are told that at time 0, at the very start of whatever this time measurement is, that our population is equal to something. So say we're told, or we discover that at t equaling 0, the population is equal to, now I'm not actually going to put in a number here, I'm going to put in this designation, P naught, P sub naught. That's just representing whatever that value is for that initial population, all right? We okay with that just kind of terminology? I mean, certainly in a certain setting, we would know the value of P naught, presumably. But there it is. You have P naught there. So therefore, let's solve for P naught. All right. So let's plug things into our equation here. Now, I'm going to substitute for P, I'm going to substitute that expression, P naught. And then I put equals, and then I put my C1. And then E to the K times, now this is the times 0, so it's to the K times 0 power. All right. Now, K times 0 is 0, so this is C1 times E to the 0 power, which is equal to 1. So this is equal to just C1. So what we find out here from this information is that our general constant C1 that we designate as C1, that's really equal to our initial population. Okay. So I can rewrite this equation like this then, substituting that P naught for C1. So I can say, thus we have capital P of T equals P naught, I'm putting that in instead of C1, times E to the KT power. All right. Now suppose, so are we okay with that? Just arriving at that from the information that we got. All right. Now say we have some more, we've gathered some more information here. Suppose, so this is talking about a population. Suppose this population doubles after T equaling 2 years. So we're measuring in years. So we somehow know this. What we're able to do with this piece of information is we're actually going to be able to solve for this proportionality constant right up there. We can now solve for K, and that's that proportionality constant. So let's try to do that. Okay, so what's our population? How can I represent our population after the 2-year span? Yeah, 2p naught. It doubles our initial population we're representing as p naught. So doubling it, it's 2 times p naught. So that's what we have on the left side. Then on the right side, we had, whoops, where is it here? Right here. We had p naught. And then we have e to the kt power. All right. So this is what we now have. Now this is p naught is a non-zero number, so I can divide both sides by that. And what I arrive at then is this equation, that the number 2 is equal to e to the kt power. And I claim that I can solve for what that proportionality constant is. So,
Why don't we put in 3? Is that not?
oh, let's see here. I'm sorry, you're absolutely right. Yep, thank you. Thanks, Cassandra. Of course we would do that. So plug in, sorry guys, so of course we would plug in the 2 for the t, t for 2, 2 for t, we would do that, all right? And let me do that down here also. Yes?
Shouldn't it be like t of 2 equals t for naught?
No, the population, so, okay, I see what you're saying. You're saying we're going to designate that population after 2 years as p sub 2. But what are we given here? We're told that this population, p sub 2, is twice our original population. We're told that, or we have discovered that. So what you're calling p sub 2, it also equals 2 times the original. So I want to use that in my equation here. Does that make sense? All right. So let me start over here with this. Then we have 2. Let me rewrite it. We have 2 equal e to the 2k. That's better. And now, how can we solve for that k? Oh, yeah. Does everybody understand? To solve for this, we take the natural log of both sides. Okay. ln of both sides. That'll get that k out from the exponent spot. So we have ln of 2 on the left side equals the ln of e to the 2k on the right side. But what does that right side end up being equal to? Okay, I know that you know this. Does everybody else understand what I can do here with the log? I can take the exponent down, right? So this is 2k times the ln of e, and we know that the ln of e is equal to 1. So we have ln of 2 is equal to 2 times k. So I want to isolate k, so I divide by 2. So I find out that my proportionality constant is equal to the natural log of 2 divided by 2. Now, if we're told to get some kind of approximation on this, this is an exact answer. If you're told, you can plug it into your scientific calculator and get, say, a 2-digit approximation of 0.35. All right. Okay. Now, the last thing for this section is that we also showed that there's a better model for population growth than this one right here. Because with that one, the population just keeps getting bigger, bigger, and bigger uncontrollably, and we know that in life that doesn't work that way. So this is another model for population growth, and we can try to solve this equation. I'm going to call this a better model for population growth. All right, and that's this following equation here. Change in population over time, dp dt, is equal to k times p, then in parentheses times m, capital M minus p. Now, k is our proportionality constant again. We're assuming that it is a positive number. And this M is like the capacity, population capacity. That's also some kind of that's a positive number also. So what I'm going to do here is, let's suppose that population capacity is equal to 50. Okay, you're given that, or you find that out. So this is our equation then. dp dt equals k, I don't know where that came from, k times p times 50 minus p in parentheses. So I'm just plugging in that 50. All right. And now we can separate the variables here. And what I need to do here, I think I need to divide by p, and I also need to divide by that parentheses expression, 50 minus p. So I can get the p's over on the left side. So I'm going to get this, 1 over p times 50 minus p on the left, dt. And on the right, it's fine. I can just keep that k over there on the right-hand side. That's just a constant number, equals k times dt. So as long as the t's and p's are separated, I can keep this. It's actually a little bit easier if you keep the k over there anyway when you do the integrating. So now let's integrate both sides. Oops. And what are we going to do to integrate that left side? The two-word answer. The first, I wish I could do charades here. Sounds like the first word starts with a P. So folks out there, it's a two-word thing. The first word starts with a P. What is it that I'm going to do on that left side? Say that more confidently, Cassandra. Partial fractions, absolutely. Partial fractions. Okay, so let's do that. Let's go off over to the side here and do that. So 1 over P times 50 minus P. Notice that this is factored. This is one factor, two factors. It's factored. It's going to equal A over the P plus B over the other factor, 50 minus P. All right? And so we cross-multiply and solve for the A and B. So I'm going to get A times the 50 minus P plus B times the P equals a 1 from cross-multiplying. Okay. What's the easy way then to figure out these A's and B's from here? Yeah, for one, let P equal 0, because that'll zero out that side. So let P equal 0. And so that gives us that A times 50 minus 0, so A times 50 is equal to 1. Therefore, our first constant A is 1 over 50. So let me put that up there, 1 over 50. And then what would be another value that I'd want P to equal in order to do this similar thing? Yeah, let P equal 50, and that'll get rid of that first term. So I'm going to just have B times 50 equals 1. So B is also equal to 1 over 50. 1 over 50. All right. So now we have two terms that hopefully we can integrate. So let me rewrite that left-hand side then as 1 over 50 over P plus 1 over 50 over 50 minus P dP with my partial fractions, and that equals the integral of K times dt. Okay? All right. So we have two terms there on the left. So the first one is going to be 1 over 50 times the natural log, right? That's 1 over P. So we have the 1 over 50, though, that we have to multiply in front. And got to be a little careful with that second one. What would that second one end up being as an antiderivative? Because we have 50 minus P in the bottom. Okay, negative 1 over 50 over what? Right. But it'd be negative 150 ln of 50 minus P, what we have in the denominator. Basically, you can check that for yourself. It's a simple U substitution where we let U equal 50 minus P, and we go from there, and we'll get that minus in front. And then that equals on the right side, well, that's K times our variable T, and then we have our plus C. All right. So, okay. Now, it is possible on this one to get an explicit solution for P. There's a lot of algebra involved in doing that. All right. I'm pretty much okay with this, but let's just do another manipulation with this just to make it look a little better. All right. What's one thing that I can do to both sides of this equation? Yeah, multiply everything by 50. That'll clear out the denominators. Why not? All right. So multiply all terms by 50. You know, if it's a legal algebra thing to do, then you can do it. All right, so that gives us just ln of P minus the ln of 50 minus P. All right, then that's going to be 50 times KT plus 50 times the general constant. Okay. Now I can do that same fiddling with that general constant. It's 50 times any number, so I could represent that as C1, where C1 is equal to the 50C, all right? So we'll just do that. ln of P minus the ln of 50 minus P equals 50 KT, and I'll just designate our general constant as a C1. And that's where C1 is equal to 50 times the C. All right. Now that's fine. There's one other log manipulation that I could do here, and then and frankly, as far as like an exam were concerned, I'd be fine with any of these representations. But what's one other thing that I can do here? Yeah, I've got a natural log minus a natural log, so I can combine it into one natural log. So that would be the P on top, because it's a minus, it would be 50 minus P on the bottom. So I have just a single natural log equals 50 KT plus the C1. And I think we'll just stop it at there. All right. Okay. So, you know, these things like integration by part, partial fractions, those are tools that just continue throughout calculus. So, you know, those are things that you need to look for that you should use if when needed. That's it then for this little mini course in differential equations. All right. Any question on just the general procedure of this? Get things separated, do antiderivatives. We only need 1 plus C. Okay. When we're given an initial condition, we can solve for the general constant. That's called a particular solution. Right? All right. Well, that's a good time. Why don't we take a 5-minute break then, and we'll get started on that other section. Susan, I put in a little order on Amazon for these. These are nice pens.
Did you teach over at Elton? Yes, 11:05.
What is 11:05? Right. I wonder if that is the kind of the quote-unquote business probability. Oh, that's my guess. Yeah. Not a hard. She said my opinion is a little biased one way. Yeah, I know. I know. Sometimes when I hand out a test, I'll say, "Well, it's not a bad test," and then I should know not ever to say that. So that's all going to be between 3 chapters, or sections of 3 chapters. Yeah, but you know, these first two, the differential equations are pretty limited to what we did there. 8 was surface area and arc length. No, there's 2 topics there, so it's not like I haven't done the top. Yeah. 10 is going to be the bulk of it, really. 10 has 6 sections. Right. That'll be the fun part. I don't know unless you've got a schedule and actually flexibility. Yeah. It's going to be pretty much at the end. I think it's going to be after Thanksgiving. Yeah. What's that? Okay, well, it's not gonna be on the Friday, it's gonna be on the Monday before that. So it says December 2nd, but it'll be, I guess that'll be,
This is starting with the sixth, so it is gonna be the second.
it says Friday the 6th,
12/6.
12/6, so it'll be 12/4. Won't that be the Wednesday then?
Yeah.
All right, you were close, Sheila. Yeah, it'll be the Wednesday, December 4th.
That's our final.
No. That's our last test.
Okay.
Final Monday, 12/9.
Yeah.
One of my friends wants to take it back, and she wants to know if you record all your classes online.
If the only ones I recorded is remote classes, the algebra class I don't record.
Okay.
She can take algebra.
Yeah, someone else.
Yeah, no, I don't record that.
Okay.
Yeah.
Okay. No, Mary. She was I mean, I certainly could, but I don't know if I'd want to. Because I think that would just, I'd be talking to unhappy people. So many. I mean, we're talking college algebra, we're talking about the majority of the folks in there don't want to be there. Right. If they can take it at home in their jammies, then that would be a lot better. But then they don't watch. Then they don't watch the video.
I didn't even show up.
Why couldn't you just test out of it then?
I mean, I could have, but my algebra skills, I felt like it was kind of.
Okay, so you just wanted a little extra practice.
Yeah, because I feel like Calc 1 and senior year of high school, I didn't get college credit for it. So I could have gone right into trades, but I needed my algebra skills to move forward.
Yeah. Okay, well, that's the basic. I mean, you've got to have the algebra skills, so probably a good idea. All right, I think we'll go on and get started here. So this chapter 10, which is the last chapter for us, basically it talks about different ways that we can either graph things or represent functions. And it's first going to start out with what are called parametric equations. Then it's going to go on to what are called polar coordinates. When you guys took trig, I thought, did you talk about polar coordinates? Yeah, good. Okay. Well, so some of that will be a review, and maybe a needed review for some of you then about polar coordinates. So it's talking about different ways to graph things and to represent. But we're going to start with this. So let's look at this. Let's look at this curve here that just goes all over the place. Okay, so we have a crazy curve like this, and on each point of the curve we have an x-coordinate and a y-coordinate. Now the problem with this curve is this: I can't represent the y as a function of x, nor can I represent the x as a function of y, because look at here. Right here, it fails the vertical line test in that direction, and it certainly fails the line test in the other direction. So therefore, it cannot be represented as either y equaling f of x or x equaling some function of y, all right? Because it just meanders around too much. But if each of the two variables, x and y, can be written as a function of a third variable, then we're in luck. But suppose x and y were each represented as a function of a third variable, and commonly we call the third variable t. All right? So what do we mean by that? So we mean that x can be written as some function of t, x can be written as x of t, and y can be written, well, let me put this as an f. Sorry, folks. Let me put that as an f of t, and y can be written as, say, a g of t function. All right? These types of equations here are called parametric equations. T is called the parameter, quote unquote parameter, P-A-R-A-M-E-T-E, right? Okay. As t changes in value, both the x's and the y's change in value. As t changes in value, both x and y also change in value. Okay. And what happens is that this x and y point traces out a curve. Traces out a curve. Okay. And this curve is called a parametric curve. Oops, this curve is called a quote-unquote parametric curve. Okay. So we have this term parametric here. We have these parametric equations for x and y. The t is called a parameter, and the curve that's generated is called a parametric curve. Okay. Now, this variable t doesn't always have to represent time, but it frequently does. Okay, but it doesn't have to represent time. So I'll just put here, t does not have to represent time. All right. So what happens with this thing, let's just look at this one here. Basically, let's say that as t gets bigger, this thing traces out in this direction maybe, this curve. So we can actually kind of put little arrows on our curve indicating the direction it's being traced out in as t, the parameter, gets larger and larger. Let's look at an example here on a PowerPoint. All right. Okay. So this example is, okay, we've got a curve, and the parametric equations are this. If x is equal to t squared minus 2t, and y is equal to t plus 1. So what we're doing is we're forming a little table here and letting the t value range over certain numbers. Notice that this table, the t starts at -2 and ends up at a +4. So what we do for each one of those particular values of t, we plug that into our parametric equation, and we get a corresponding x value and a corresponding y value. So that's what we have on the next two columns, are the x and y values that are generated from those different t values. So let's look at what the curve looks like here. So this is showing the curve that gets traced out as we do this. And this dot right here, that's when t is equal to -2. And notice we've got this little arrow. And then we hit this other dot here where t is equal to -1. And then we keep going along. Here at this dot, t is equal to 0. And we have other dots as t gets bigger and bigger. The arrows on the curve that's created represent the direction as it's being formed as t gets bigger and bigger. Okay, so that's why we have the arrows. I don't know how distinctly you can see those arrows. They might look a little fuzzy. But trust me, the arrows are pointing in this direction, all right, as it goes along. Okay. Right. Okay. Oh, actually, I shouldn't have taken that up quite so soon. But if you can, let's look at this thing again. All right. If you look at that curve, it kind of looks like a parabola on its side, doesn't it? So I just wanted to point that out. It kind of sort of looks like that, all right? So that's what I wanted to say on that. So let's look at something here. Okay, so the curve sort of looks like a parabola. Sort of looks like a parabola. And actually, we can verify that it really is. So let's verify this. Now, the way we're going to verify this is we're going to replace those parametric equations with a single equation in just x and y. So we had this. We had that, x was equal to t squared minus 2t, and y was equal to t plus 1. All right, we're going to do some substitution here to get everything as one equation. So if y is equal to t plus 1, if I can solve for t, therefore t is equal to y minus 1. All right? Now, I can plug this value for t into the other equation with a substitution. So now we have x equal, now that t is y minus 1, so I'm going to use parentheses because I'm squaring that first term, minus 2, and then I'm going to use parentheses again to put my y minus 1 in there. And then let's expand it out and see what this thing looks like. So x is equal to, okay, when we FOIL this out, it's going to be y squared minus 2y plus 1. And then let me distribute the minus 2. I have minus 2y plus 2. And now let's combine common terms. So we have y squared, let's see, minus 4y. And 2 plus 1 is 3. All right. So we have this. So basically, our x-coordinate here is a quadratic in the other variable. So that's why it's a sideways leaning parabola. All right. Now, this equation that we get has a name. It is called the Cartesian equation. This is called a quote-unquote Cartesian equation. You may or may not have heard that when we look at this terminology, when we are looking at the x and y graph, the points on this graph are called, have you heard this term, Cartesian coordinates? If you haven't, you're hearing it now. These are called Cartesian coordinates. So since the equation is now in x and y, it's called a Cartesian equation. All right. So the first equation we had was called a two parametric equations. What we now are representing the curve by is a single Cartesian equation. All right. Now, sometimes we don't want t to be any number. Sometimes we want to restrict the values that a parameter t takes on. So let me put this down. So sometimes we may restrict or want to restrict t, the parameter, to a finite interval of numbers. Okay. Maybe it's some kind of experiment. We're not interested in t going beyond any certain length period of time. All right. So basically, what we can look at, from the previous curve, so let's just look at t going from, say, 0 to 4. So I'll put this up on the screen here. So we're looking at that previous equation that we had, parametric equation. But now for whatever reason, we're just wanting to restrict our t value, from I don't know why, from 0 to 4. So what we get here with this is we just get a partial representation of that curve, all right? Because here is where the t was 0. Here's where the t was equal to 4. And if you can tell or not, the arrow is going in that direction there on that. When we are doing something like that, these two endpoints have a name. Where we are starting is called the initial point. Where the curve is ending is called the terminal point. All right? So we have these two things, initial point and terminal point. Okay. Let's look at another example here. Here's another example. So here's our parametric pair of equations. X is equal to cosine of t, y is equal to sine of t, and so t is our parameter, and we're letting t go from 0 to 2 pi. That's our range for the t. All right, so we're restricting the values of t. All right. Anybody have an idea of what this is going to look like once we graph it? Remember, in trigonometry, it has two words, and the first letter of the first word is U. The first letter of the second word is C. Trigonometry.
You're going to pay for and I'll write down the
Nope, no ideas. Any ideas for that, for the answer here? What's going on here?
So if I know the answer.
I know, I'm trying to read the screen. Crazy. There we go. Samuel McNair, type, unit circle. And you're absolutely correct. Does that ring a bell now? Unit circle? Okay, unit circle from trigonometry. All right, so actually let's look at something here. Let's go back to a PowerPoint. And so you guys see it? I don't know why it's not showing up there. All right, here we go. All right. So this is what's happening here. So our x and y coordinates here along this curve are cosine of t and sine of t. So this should look very familiar. And our starting point is right here when t is equal to 0. And it goes, as t gets bigger, it goes in this counterclockwise direction. And when t is equal to 2 pi, it ends up right where it started. So the initial and terminal points meet each other as a circle. Okay, this t here that keeps varying, that can be thought of also as the angle of the cosine and sine using the radian measure, okay, in terms of pi. And of course, this is the unit circle from a trig. So that's the kind of thing that we get when we just plot some points and connect it. We'll get that unit circle. Okay? All right. Okay. Almost have to kick it. All right. Let's actually ask ourselves now, okay, we got the unit circle. Let's find the corresponding Cartesian equation. Let's find the corresponding Cartesian equation. And this is what we're going to get. Okay, x is cosine of t, y is sine of t. Well, what happens when we look at x squared plus y squared? Okay, well, x is cosine, so that equals, oops, that should be an equal sign. Well, x is cosine of t, and we're squaring that. Y is sine of t, and we're squaring that. And what's the value of cosine squared plus sine squared? 1, right. So what our Cartesian equation is x squared plus y squared is equal to 1. And this is certainly the equation of a circle with radius 1. And the center of this circle would be the origin 0, 0, okay, from algebra. Okay. All right. In your homework, you'll have a couple of problems where you're asked to find the corresponding Cartesian equation. Let's look at another example here. First of all, here's our parametric equations. X is equal to the sine of t. Y is equal to the sine squared of t. And t just keeps going and going. All right. Let's say it starts at 0 and then goes from there. Okay. Now, if we want to try to just see what this might look like, we can do find what the x and y points are. And let's just start with t equaling 0. So when t is equal to 0, x is the sine of 0, which is 0, and y is the sine squared of 0, so that's also 0. All right? Now, let's pick some values for t where we can get easy signs for. So let's just go right on to pi over 2. So at pi over 2, the sine is equal to 1, and the sine squared would also be equal to 1. Now let's jump to pi. Now, at pi, the sine of pi is what? It's 0, and so is the square of it. And then let's look at the 3/2 pi. So we're looking at all the different quadrants here. When sine of 3/2 pi is going to be what? -1. And now the square of it, however, is going to be a +1. And then let's just go back to 2 pi then. 2 pi. And the sine of 2 pi is 0, and so the square is 0. So we've got some xy points here. So let's just get an idea of what this thing looks like. So it starts out where 0, 0 right here. Let me put a marking on. This is 1, and this is 1, and this is -1. All right. And then the next point is 1, 1. Now, is this going to be represented by a straight line or some kind of curve? It's going to be a curve, right? It's going to kind of look like this. And then that's our next point. So it went up like this, so we put the arrow in that direction. So now we're at 1, 1. Now we're going to go back to 0, 0. So what's going to happen is we're going to then traverse back that same curve to get back to 0, 0. And then we're going up to -1, 1. So it's going to go up, up like this. And then we're going to go back to 0, 0. And it's going to go back down there like this. So what this little curve keeps doing is it just keeps going back and forth and back and forth and back and forth as t gets bigger and bigger, right? Okay. Let's find the corresponding parametric equation, Cartesian equation. So the corresponding Cartesian equation. All right, well, let's see. We have x is equal to sine of t. Y is equal to sine squared of t. So what can we get here? Let's see. Y is equal to sine squared of t. But sine of t is equal to x, so sine squared of t is equal to x squared, right? So here's our corresponding Cartesian equation. It's y equaling x squared. Now in this case, we notice that it doesn't keep going, so this is for x less than or equal to 1 and bigger than or equal to -1. So it's limited. It just keeps going back and forth on that little arc there. Okay. Everybody see how I got the corresponding Cartesian? Doing a little substitution. All right. Here's another example. All right. Okay. We'll do this one here. Sketch the curve with the parametric equations, with the following parametric equations. The following parametric equations. Okay, here we're told x is equal to t squared minus 2t, and y is equal to t squared plus t. All right, and we're told here that we want to restrict t from -2 to +2. So it's only going to be a certain limited curve. All right, so the way to do this is to set up this table of x and y's and do the t values. Just do the t values at the whole numbers. So we just start with the smallest t value, -2, and we plug this value into both of our equations. Now, I'm not going to just do all the arithmetic here. I get an 8 and a 2 here. The only thing that I can warn you about in this case is to be careful because it's a negative number, so don't mess up on the basic arithmetic on it when you figure out the value. And then when t is equal to -1, we end up with 3 and 0. When t is equal to 0, we get 0 and 0. When t is equal to 1, we get -1 and 2. And finally, when t is equal to 2, we get 0 and 6. So we've got, 5 points there that we can put on a graph. And so let me do that. On some of the homework here for this section and other sections, you're going to need to have some graph paper, by the way. I do have, I can make a whole bunch of copies of graph paper for you folks here. I did put basically a PDF of this particular graph paper on Blackboard. If any of you Lafayette or Eureka people want to print it out and make some copies of it, or if you have your own graph paper, that's fine. But let's see what we get here with this. So, okay, so our first point here at -2 is x is 8, y is 2. So we have that point right there. And then the next point is x is 3, y is 0. So we have that there. And then we have 0, 0. So we've got that there. Then we have -1, 2. So we have that point. And then finally we have x is 0, y is 6. All right. So so the curve is going this way. All right. So let me attempt to join these with something that resembles a smooth line. Okay, and I just have some arrows on it to indicate the direction that the curve is going. So that would be my representation on a graph just from those x and y values. All right. Okay. I think then, I wonder if that's going to work out for this point here. All right. Notice that on this particular problem, I'm not trying to get the corresponding Cartesian equation because I think it would be very difficult, if not impossible, to do that. All right. So if you want to try, fine, and I'll be very impressed. But I don't know if I could do that. All right. That's why I've just kind of not mentioned it until, well, I did mention it. But, okay. The last thing then in this section is that one. Is just looking at a couple of parametric equations and trying to find the corresponding Cartesian equation. So we'll just call these finding the corresponding Cartesian equation. All right. So there's two examples here. For A, we're given that x is equal to e to the 2t power, and y is equal to t plus 1. And I'm claiming that we can get a corresponding Cartesian equation in x and y. All right. Any thoughts on any manipulation manipulations we need to do to one of these initially. Notice in that first equation that t is in the exponent department, exponent area, right? Now, it's hard to work with something that's in the exponent area. So how can I move that t down from the exponent spot legitimately? Yeah, if I take the natural log of both sides of that equation, I can do that. So let's take that equation and take the natural log of x, the left side, equals the natural log of the right side. And then I can move through the rule of logs and move that 2t down below. So I have ln of x is equal to 2t times the natural log of e, but that's just equal to 1. So I have ln of x is equal to 2 times t. Now, we want to isolate, we want to end up going into the next equation, t plus 1. So I want to isolate the t here. So I'm going to divide both sides by 2. So I get that t is equal to the natural log of x divided by 2. And then I'm going to go and plug that into my other parametric equation, y equals t plus 1. So now I'm going to have y is equal to the natural log of x over 2 plus 1. And that would be my corresponding Cartesian equation in x and y.
Does it matter which one you get by itself first?
No. Okay, in other words, I see. You get the same thing. So Nikesha's asking, could I have worked the other way? And you could have. I could have said, okay, t is equal to y minus 1 from the second one, and then go to the first one, and I have x is equal to e to the 2, and then in place of t, I'll put my parentheses y minus 1, all right? Then do the natural log, and that'll give me 2y minus 1 times the ln of e, which is just 1. And let's see, okay, that's actually the same equation. It's just written differently. This is the same equation as the other one. Okay. You all right with that? Okay. Actually, this one I could even use the base e and actually have it as x as e to the power and that type of thing. Maybe I should just show that just for the heck of it. I could take both sides with the, use the spiral with the base e. So I have e to the 2 times y minus 1 power. Complete the spiral equals x. So I have an equation of x in terms of y like that. It is. It's exactly the same thing. You're right. Thank you for noting that. That is right. I just got back to where I was.
I just want to know if it matters.
Oh, I see. Oh. No, it doesn't. In fact, now that I'm looking at this thing, I could have just stopped, right here. Okay? And it does not matter. Some equations are better suited to put it in y in terms of x, others x in terms of y. Right? But that's perfectly fine. All right, one more, and that'll be it for this section, what I want to cover in this section then. And it's the same kind of problem. So here we're told that x is equal to the tangent squared of theta, and y is equal to the secant of theta. And we want to get that as a single equation in x and y. So we have some kind of relationship between tan squared and secant. Well, tell me first of all, just what is the trig identity that involves the tangent and a secant, tangent squared and a secant of some kind. Right. So Cassandra says, yes, 1 plus tangent squared of theta equals secant squared of theta. That's the identity that I can use here, all right? So we use this trig identity. So certainly for the tangent squared, notice the tangent squared is just equal to the x, so I have 1 plus x. Now on the other side, it's secant squared. Now my y is just equal to the secant, so I have to square it to represent secant squared. Like that, all right? And then if I wanted to, I could isolate just x on one side by subtracting 1, and I could have it written like that. And this would be a good example of an equation that's more naturally suited, in this case, to be written as x in terms of y, right? And equations like this, then, if you were to graph this thing, this would end up being a sideways parabola. It would look something like that when you graphed it, right? Okay. And that's all I wanted to say then on this introducing parametric. So what we're going to be doing then on Monday is we're going to be doing some calculus with parametric equations. We're going to be finding derivatives of the curve. We're going to be looking for the formula for arc length and the formula for surface area of a revolution. So things from that previous section in chapter 8, we're going to be looking at those things, and that'll be our 10.2. All right? So that's it for today then. I think I might as well just stop here. Unless you demand that I continue. I was expecting at least one person to demand that I continue.
Friday.
If you're turning in that 5-point thing, please do so. Yep.
Well, I think that I think I like what you're saying.
What is this now? Oh, are you squibbling about a grade?
Yeah.
Which one?
This one's mine from the solution manual.
Uh-huh.
But I have the same thing.
Oh, let's see, what? Okay, you have this going down to 0. Yeah, you're right. I'll give you a point. Oh, no. It's only worth 4 points.
Yeah, I mean, you didn't give me any. You said plus 0.
Oh, did I?
I wrote that on there.
My
And
okay.
I had a question about...
So let me make a note to myself before I forget. Hold on. All right. So you can go from a 111 to a 115. All right.
Okay, and this is like the same.
Oh no, we're doing something else here. What is this now? Wait.
If the series of divergence and the limit is not equal 0, isn't that the same thing?
No. Mm-mm.
Why? Because if it's convergent, then it equals 0.
No. Mm-mm. I'm going to show you an example. The harmonic series gets divergent, right? So what's the limit?
Yeah.
So here we have this example of a series that is divergent, but the limit equals 0. So it's not the same thing. Not. See? If there is a counter example, it is not true. All you need is one. All right. But I messed up on the limit. Absolutely. If it's